Hi, everybody. So this is going to be a quick overview of the concepts covered in Exam 1 and Exam 2 for APPM 2360, differential equations and linear algebra. This isn't intended to be a comprehensive or thorough review. This is just a bit of a refresher of the important equations and concepts that you should know from each of these exams going into the final. Yeah, let's get started. Welcome to my review for the APPM 2360 final exam. We are going to be covering all the material from Exam 1 and Exam 2 in this part. So without further ado, let's get started. Let's talk about Exam 1. Okay, so the first concept that I think we should discuss is the integrating factor, or integrating factor. And so this is when you have a differential equation of the form y prime plus p of t times y is equal to some function q of t. And so the integrating factor, which I'll denote here as if, we use a symbol mu of t, and it's equal to e to the power of the integral of p of t dt. And so the method that you want to use is you'd want to multiply both sides of the differential equation. So I'll write it in this form. It'll be mu of t y prime is equal to the integral of q of t times mu of t plus c. Don't forget this plus c. And so you'll see that if you actually expand this out, you get the left-hand side of this equation. So after you go through with that, you can then isolate for y. Okay, next thing we want to cover. Let's talk about the superposition principle. Superposition principle and I'll call it the homogeneity principle. Okay, so superposition, there's two important points. So one is that if y is a solution to our differential equation, a constant times that y, c, is also a solution, given that c is a real number. And the second thing we need to note about the superposition principle is that if we have two solutions, y1 and y2, then their sum, y1 plus y2, is also a solution. Sick. Let's move on to the non-homogeneity principle, or non-homogeneous principle. Non-homogeneous principle. So if you have, actually before that, let's define what a homogeneous differential equation is. So homogeneous dE. So I want you to consider the nth order linear ordinary differential equation with constant coefficients. That was a mouthful. Let me write that down. So consider nth order. We'll get to each of these parts in turn. Linear ODE with constant coefficients. And this will be an equation of the form something like y of n, y to the nth derivative plus a n minus 1. That should be a subscript times y to the n minus 1th derivative. That should be a minus 1 plus a bunch of other terms plus a1 y prime plus a naught y is equal to some forcing function f of t. Let me just move this to the center. There are two parts of a general solution. So the general solution y is made up of two parts, something called y sub h, the homogeneous solution, and y sub p, the particular solution. And so now let's get into each of these parts. So y sub h is what we call the homogeneous solution, And this is when f of t is equal to 0. So if we just set this to 0, we can use a lot of the skills that you've learned throughout the course of this class, like, you know, the Euler-Lagrange, integrating factor, whatever you want to do to solve the differential equation. Y sub p is what we call the particular solution. And this is any solution that satisfies the differential equation. So any solution that satisfies the DE. Okay, this is a good lead-in to the next topic, Euler-Lagrange. Euler-Lagrange. Okay. So, and this is for differential equations of the form y prime plus p of t, y is equal to q of t. So we have our general solution y equal to yh plus yp. This is from the non-homogeneous principle. We need to determine both what yh and yp are. So let's do that here. Yh we'll figure out here. Yp we'll figure it out over here, and I'll just put a little divider in between the two. So with yh, we just substitute, instead of y into this differential equation up here, we're going to sub in y sub h. So this differential equation then becomes yh prime plus p of t times yh is equal to q of t. Or in this case, because it's the homogeneous solution, q of t is just 0. And if you solve this through, what you'll get is, let me just rearrange this a bit. Excuse me. Oh man. What you'll get is y sub h is equal to c, a big C, e to the negative integral of p of t dt. And this c over here, this big C is from e to the c. So after you integrate this out, you have the plus c. We just take e to that power, it's just some constant. For yp, what we want to do is we want to, let me move this to the side a little bit. Excuse me. We want to replace c with a function v of t in our solution for yh. So we're just going to take this exact solution over here, and just instead of a constant, we're going to use a function. So we plug it into the original differential equation, this guy up here, in the same exact way, and what we get is yp prime plus p of t, yp is equal to q of t. And substituting in, this will become v, where v is a function. So this is v of t times, actually, yeah, it'll be v times yh prime plus p of t times v times yh is equal to q. And what we'll want to do, the general approach is that we isolate for v prime and we integrate. And remember, no plus c. This is something that I struggle with myself. And so this may not be that concrete to you, but I think that let's go over an example that I think will help. For example, let's do y prime minus y is equal to e to the power t. Let's first solve for our homogeneous solution, y sub h. Plugging it into our differential equation, this becomes y sub h prime for this part minus y sub h is equal to 0 because it's the homogeneous solution. And just for clarity, let me rewrite this as dy sub h over dt. That's just yh prime minus yh is equal to 0. We can rearrange that, and you'll get dyh over yh is equal to dt. And solving that out, you get the natural log of the absolute value of yh is equal to t plus c. Once again, we rearrange, and we find that y sub h is equal to c times e to the t. That'll box this for now. Now let's solve for our particular solution, y sub p. So y sub p, we're going to take our solution here and replace c with v times e to the t. And just remember, this is v of t. It's a function. It's not a constant. So then we can solve, we can plug it into the overall differential equation. We'll say yp prime minus yp is equal to e to the t. Plug in our solution for yp with the v of t. This will become, so v times e to the t prime minus v times e to the t is equal to e to the t. And then we can expand this just using the rules that you guys probably learned in Calc 1 or Calc 2. This will be, with the product rule, this is v prime e of t plus v and e of t prime is just e of t minus v times e of t is equal to e to t, e to the t. These two cancel out. And so our resulting differential equation is v prime times e to the power t is equal to e to the power t. This implies that v prime is equal to 1, which means that we can then conclude that v is equal to t. You're just integrating it. So going back to our original equation up here, we have y sub p is equal to v times e to the t, and we know that v is equal to t, so this is t times e to the t. And we can then plug that into our general solution. So y, we know that y is equal to yh plus yp, which means that y is equal to c times e to the t plus t times e to the t. And that's our final general solution. Okay, sick. Moving on. Let's talk about Picard's existence and uniqueness theorem. Not the guy from Star Trek, some other person. Picard's existence and uniqueness theorem. So let's say you're given some initial value problem. So you're given the IVP that y prime is equal to some function f of both t and y, and you're given the initial condition that y of t naught is equal to some value y naught. What you can say about this function is that if f is continuous around this point t naught y naught, so if f is continuous around t naught y naught, then you can say that a solution exists, a solution to your overall differential equation. Now, if f sub y is continuous, and this is f sub y is the same as just partial with respect to y of f of t. So f sub y is continuous around t naught y naught, then what you can say is that the solution is unique. So the solution is unique. And again, I think this is better illustrated through the use of an example. So let's take the differential equation y prime is equal to root y, and the initial condition y of 0 is equal to 0. So this is our f of t. So f of t and y is equal to root y, and this is continuous at 0, 0, which means that a solution exists. If we take the derivative with respect to y, so f sub y of t and y, this is 1 over 2 root y, and it is not continuous at 0, 0, which means that uniqueness is not guaranteed. We can't conclude anything from this. So uniqueness not guaranteed. I don't know if I spelled that correctly. Okay, moving along. Let's talk about Euler's method. And so if you watch the movie Hidden Figures, you've probably heard that, oh, Euler's method, that's ancient. It's ancient, but it works. And I forget the actor's name, but he was Sheldon in Big Bang Theory. That's BS. We use Euler's method all the time. It's one of the most reliable ways to numerically solve differential equations, and it's simple. So you're given some initial value problem. Let's say y prime is equal to f of t and y of t naught is equal to y naught. That's our initial condition. What we can do is we can set up an array that, every tn plus 1 is equal to tn, our initial time step, plus what our step size is, h. And then each iterative value of the general solution, so yn plus 1 is equal to the previous solution, yn, plus our step size, h, times the differential equation function, so f of t of n, y of n. Okay, next we're going to cover the logistic equation. So we're getting way more into applications now. So there's three main applications that I think they covered, or maybe four. You've got logistic growth, you've got Newton's law of cooling, you've got mixing, and you've got compound interest. So let's start off with the logistic equation. This is just a differential equation of the form dy over dt is equal to r times 1 minus y over L times y, with the initial condition that y of 0 is equal to y naught. The general solution to this form of differential equation is y of t is equal to a big-ass fraction, 1 plus L over y naught minus 1 times e to the negative rt, with L on the numerator. Next application we're going to cover is Newton's law of cooling. So with Newton's law of cooling, we're given a differential equation of the form d big T over d little t, so the change in temperature over time, is equal to some constant k times m minus t, and k is going to be positive. You're also given the initial condition that t of 0 is equal to some initial temperature t naught. And because I always found this notation a little bit confusing, so I'll just outline it here. M here is the temperature of the surroundings, and T is the temperature of your object. And the way you can solve this is that you can solve using the integrating factor method. So solve using IF. So let's rearrange this into a form that we're familiar with, d big T over d little t plus k times t is equal to km. This is just a rearranged form of the same differential equation. We apply the integrating factor method, which I won't get into here, but your end solution is going to be t is equal to m plus t naught minus m e to the negative kt. And I think this would also be better expressed with an example. So I'm gonna quickly just drop this example in here. So say we have a turkey in the oven, and the oven is at 185 degrees Fahrenheit, and we put it at a table, which is at room temperature, 75 degrees Fahrenheit. We know that the turkey is 150 degrees Fahrenheit after half an hour, so we want to find what the temperature is going to be at 45 minutes. The other thing we want to find is at what time will the temperature be 100 degrees? Before we get into this, I want you to note that 45 minutes, so 45 min, is equal to 3/4 of an hour. This will make our lives a little bit easier going forward. So what we want first is a general expression for t over time. General expression for t of t. And so we can just take this formula we defined up here and say, okay, I know that my T naught is equal to 185 degrees Fahrenheit, that's my initial temperature, and my surroundings, M, it's at 75 degrees Fahrenheit, and let's say the units for T are going to be in hours. I can then plug this in, and I get that T is equal to M plus, let me just write out the whole expression before I plug anything in, e to the negative kt, which is equal to 75 plus, if you simplify that, that becomes 110 e to the negative kt. Okay, now we need to figure out what is k. we know that t of half an hour is equal to 75 plus 110 e to the negative k, or that should be k, times half an hour, and that's equal to 150. You solve this out. What is that? So 75 over 110 is equal to e to the negative k over 2, which means that k is equal to negative 2 natural log of 15 over 22. Sick. And now that means that our general solution is t of t is equal to 75 plus 110. And I'm just going to pull some logarithm tricks. Like you can simplify this expression, rearrange it, and then what you end up getting is 110 times 15 over 22 to the power of 2t. Okay, so we wanted two things. One of the things that we wanted, let me just make this like that. Okay. One of the things that we wanted was t after 3/4 of an hour. The other thing that we wanted the t for temperature to be 100 degrees Fahrenheit. So t of 3/4 is just 75. All we do is plug this in times 110, 15 over 22 to the power of 2 times 3/4. And if you solve that out, you'll get that the temperature is about 137 degrees Fahrenheit after 45 minutes. This other thing here, all we're going to do is sub in 100 for t. So this will be 100 is equal to 75 plus 110, that's 15 over 22, to the 2t. Let's solve that out. Let's do this. 25 over 110 is equal to 15 over 22 to the 2t. And if you solve that out, you should get your t approximately equal to 1.93 hours, which sounds about right. Okay, second to last application we're going to cover is mixing. Fun fact, this is the stuff that my dad did his PhD in. So for mixing, let's say that let's denote x as the amount of solute. And so this is a sort of situation where, you have your tank, you have some amount of solute, you have a flow in, you have a flow out, they may not necessarily be the same. We can set up an overall balance. So overall balance on x. The rate of change of x over time in your tank is equal to the rate of x in minus the rate of x out, which the rate is equal to whatever your concentration is in times your volumetric flow rate in minus your concentration out times your volumetric flow rate out. And the concept isn't too hard to wrap your head around, but to give it more concreteness, let's go over an example. So let's say we have a 300-gallon tank. You have 2 pounds per gallon coming. That's your concentration coming in, and the rate it's coming in at is 3 gallons per minute. And you have your solution leaving at 2 gallons per minute out. And what you want is a general solution. The initial condition I'll give is that you have 50 pounds of X in the tank initially. Now, this is just a good practice for engineering in general, but specifically with this problem, because I'm a chem bio engineer, this is my jam. So let's draw out our tank. Drawing diagrams, always a good practice. I have my tank, I have my little rotary mixer there. I'll have 3 gallons per minute in, and I'll have 2 gallons per minute out. And I have 300 gallons in my tank. So we start this problem by writing out a volume balance. So the rate of change of volume, V, over time is equal to my volumetric flow rate in minus my volumetric flow rate out. And this is going to be in units of gallons per minute. my volumetric flow rate in is, oh, crap. My volumetric flow rate in is 3. My volumetric flow rate out is 2. So we know that dV over dt is equal to 1. And I know my initial condition, my volume at time 0 is just 300 gallons. And so integrating this, you just get that V of t is equal to t plus c. Can't forget the constant integration. We're going to plug in this initial condition right here. And so 300 is equal to time equals 0 plus c, which means that c is equal to 300, which means that our overall energy, our overall volume balance is going to be T plus 300, and this will be in units of gallons. Now, let's write a solute balance. So let me move this up a little bit. So let's write out our solute x balance. My rate of change of x over time is equal to my rate of x in minus my rate of x out. And that's equal to my concentration in is 2 pounds per gallon times 3 gallons per minute. You can see here the units will cancel. You'll get units of pounds per gallon, or pounds per minute, sorry. And then the concentration out, so I want x of t, x at a certain time t, over my volume at a certain time t. I don't know what x of t is, so I'll leave that there. That's what we're trying to figure out. And my volume is given by this expression that we just determined, t plus 300. So t plus 300, and this will be pounds per gallon. And my flow rate out is 2 gallons per minute. And so you can solve this out, and you'll get dx over dt is plus 1 over 300 plus t x is equal to 6. And your initial condition is that x of times 0 is equal to 50. From this information, what you can then do is you can just do the integrating factor and plug in your initial condition to get your solution. Okay. Last thing, last application, and then we can move on to the stuff in exam 2. Last application is compound interest. So compound interest, especially of interest if you have a bank account or a credit card or buy and sell things regularly. I don't know. There's 3 different types of formulas you may see. So one is annual. You have continuous. This is the types of interest. So you have annual interest, you have continuously compounding interest, and you have periodic interest. And so I'm just going to give you the formulas for each of these. For annual, it's the simple A is equal to A naught 1 plus R to the power T, where T is number of years. Continuous, A is equal to A naught times E to the RT. And then periodic, it's A is equal to A naught times 1 plus R over N to the power of NT. And here, this is when you have your interest N times per year for T years. Sick. The last thing that we'll cover is the savings problem. And I won't make a new section. I'll just put it underneath compound interest because the concepts are quite similar. So savings problem. You're given a differential equation of the form dA over dt is equal to r times a plus little a. And the initial condition the initial a is a naught. The general solution to this is going to be a of t is equal to a naught e to the rt plus little a over r e to the rt minus 1. And just as a refresher, r is going to be your annual interest rate, and then a is going to be your yearly increased deposit. Okay, that covers everything that we need to know for, or not everything, but that should be broad strokes the concepts that you covered for exam 1. Let's get into exam 2. And actually, before we get into exam 2, I'd like to, oh crap. So before we get into exam 2, I just want to refresh matrix multiplication. Say I have two matrices, A and B. A is an M by N matrix, and B is an N times P matrix. You can only multiply them together if the inner dimensions match. And if you do multiply them together, the resulting matrix will have dimensions M by P. Okay, so let's start off our discussion by talking about invertible matrices and the determinant. So invertible matrices and determinant. So when we say that A is invertible, what that means is that the inverse of A exists, and that we can also call this non-singular. This also means that if A is invertible, AX equals 0 only has one solution. It only has the solution of the 0 vector. And then we can say it is not invertible or singular if the determinant of A is equal to 0. And determinant is just this. I'm not going to outline the operation, but we can, well, I'll cover some properties of invertible matrices and the determinant. So properties of invertible matrices and determinant. So the determinant of A transpose, if the determinant of A transpose is equal to A, that means that the inverse of A transpose is equal to the transpose of A inverse. If the determinant is not 0, so the determinant is not or non-singular, should close that, then we can say that the determinant of A inverse is equal to 1 over the determinant of A. So the reciprocal. Last property that we're going to cover is that if we have two matrices, A, B, and we want to take its inverse, that's just equal to inverse B times inverse A. And recall that for matrix multiplication, the order does matter. Next thing we're going to cover is the transpose. And this is just where you flip your rows and columns. And some properties of the transpose. Properties of transpose. I'll just call it properties. So I can say A transpose transposed is just A. If I take some constant and I multiply the matrix by that, and I want to take the transpose of that, I can just bring the constant outside. It's just K times A transpose. If I'm adding two matrices, A plus B, and I want to take the transpose of this quantity, this is just equal to A transpose plus B transpose. And if I multiply two matrices, A times B, and I want to take their transpose, this is B transpose times A transpose in that order. Another quick note, if A transpose is equal to A, we can say that the matrix is symmetric. Okay, next thing, Cramer's rule. So this is a way to solve linear algebra problems. We want to solve the classic problem. We want to solve AX is equal to B. This is every problem in linear algebra. And here we're saying that A is not singular, so the determinant of A is non-zero. For each I, and for this I mean your solution X, it's just a sum of a bunch of, or you have X1, X2, all the way down, Xn. And so for each of these, I'll call these Xi's. So for each I, replace the ith column of A with B, and we're going to call this A sub I. The corresponding entry in your solution vector, x sub I, is going to be the determinant of your new matrix A sub I over the determinant of A. Okay, let's talk about, that didn't work. Let's talk about minors and cofactors. So minor and cofactor. So for this, let me say we have this example matrix. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9. Minor and cofactor is just a small section of the matrix. So let's say I want minor 1, 1. What I'll do is I'll block out the first column and the first row, and I'll take whatever's remaining. So this is just going to be 5, 6, 8, 9. I'm going to get rid of this. That is my minor. My cofactor C11 is equal to -1 to the power of I plus j. In this case, both of them are 1, so 1 plus 1. And we'll multiply that by the determinant of my minor, 1, 1. And if you solve that out, you should get -3, I believe. And the reason we care about this, the cofactor, is that we can use this to calculate the determinant. So use to calculate determinant, where determinant of A is equal to the sum of all Aij times their corresponding cofactor, Cij. Okay, let's start talking about vector spaces, everybody's favorite topic. So they'll probably throw some sort of question at you about, let me move this up a bit. Yeah, whatever. So verifying vector spaces. And this is the double bar V. There's two requirements that a set of vectors is a vector space. So the first one is closure under linear combination. Closure under linear combination. That's just a bunch of fancy words that says, hey, if I have two vectors, x and y, that are part of, or that are said to be part of my vector space, and I have two constants, CD, that are real numbers, then I can say that if I multiply constant by x plus a different constant by y, or just some constant by y, this resulting vector should also be part of my vector space. That's what closure under addition, or that's what closure under linear combination means. It's closure under multiplication by a constant and closure under addition. The second thing that we need is the existence of the zero vector. And so this will lead us into the vector subspace theorem. Vector subspace theorem. Okay, so if I have some non-empty subset, so non-empty subset, not subspace, subset, I'll call this W, which is a part of our vector space V. W is a subset, or sorry, a non-empty subset W that is in our space V is called a subspace. It's called a subspace of our V if and only if it's closed and the zero vector exists. And so the two tests that we're going to use for that, or three tests, sorry, we want to check that if U and V are both vectors in W, that their sum, U plus V, is also in W. So that's closure. if let's closure under addition, if U is in our subset W, and we take some constant C, which is a real number, C times our vector U must also be in our subset. And the third is that the zero vector exists. And if you can prove all these three, then it is your subset W is called a subspace. Okay, let's move on to talking about linear independence. So testing for linear, I'm going to use this symbol to mean independence, because it's a long word and I don't want to have to write it. So let's say we start off with this matrix A. That's it's a bunch. We can consider A to be made up of a bunch of column vectors, v2, a bunch of other rows, vn. So this is A. And then we also have our vector x. This will be c1, c2, all the way down until cn. And we want this to equal 0. Okay, so that's the equation we're going to deal with. We can say that our column vectors are linearly independent if and only if the trivial solution x, so the solution to this is only when x is equal to the 0 vector. So that's what we call the trivial solution. So if trivial solution, where x is the 0 vector, is unique, it's the only solution to this equation. And that means that every, all the CIs is 0. So every CI is 0 for all I. And what this implies is that A is invertible, the determinant of A, following consequence, is non-zero, and that A has n pivot columns. I'm not going to get into what pivot columns are. Let's talk about linear dependence of functions next. So linear dependence of functions. Okay, so I have a set of vector functions. So let me say vector functions. I've got, oh man, let's say v1 of t, v2 of t, bunch more all the way up to vn of t. These are linearly independent if c1 v1 plus c2 v2 plus a bunch of other terms just like that plus cn vn is 0 only when ci is 0 for all I. And this has to be the unique solution. So this is getting more into a little bit of what you covered on the third exam, but we're going to talk about the Wronskian and testing for linear independence of a set of functions. So let's say I have a set of functions. That was terrible. f1, f2, all the way up to f of n. And so the key idea here is that if it holds true for all t, it must hold true for a particular t. Okay, so I'll show you the formulas that we care about first, and then we're gonna get into the nitty-gritty of what it is. So if the Wronskian, so W, is non-zero for at least one t, it's linearly independent. If W is 0, we can't conclude anything. So no conclusion. And just as a quick refresher on what the Wronskian is. So Wronskian, let me just make sure that this is clearly a note. So let's say our set of functions is, I want to calculate the Wronskian of a set of functions f1, f2, all the way up to fn of x. And the important thing to note here is that these functions f, all of them are n minus 1 times differentiable on some interval of I. The Wronskian is determined as the determinant of a very special matrix. So we're going to put all of our functions, f1, f2, all the way up to fn. And then in the next row, we're going to take the first derivative. So f1 prime, f2 prime, dot, fn prime. It's bothering me that this has 4 dots. And then we're going to keep taking derivatives. So eventually you're going to get to the n minus 1th derivative. And f1 n minus 1, f2 is n minus 1th derivative, and fn's n minus 1th derivative. And so if you take the determinant of that, that'll give you the Wronskian for x on the interval I. Last thing we're going to cover, just a bunch of definitions. So I'll just write here. Various definitions. So we refer to as span. This is the set of all linear combinations of vectors. The set of all linear combinations of vectors. And this leads into the span theorem, that if we have a set of vectors, v1, v2, all the way up to vn, these are all vectors that are members of our vector space V, members of our vector space V, then the span of my set of vectors it's a subspace of V, not a subset. Well, it is a subset too, but it's a subspace of V. And the importance of subspace is that it has closure and the zero vector exists. Okay, dimension. So it's the number of vectors in what we call the basis. Number of vectors, let me move this up, in basis. And so a particular example that we can analyze is this set of polynomials, P sub n. So the dimension, our polynomial space of P sub n is n plus 1. Okay. Quick review, basis. If I have a set of vectors, v1, v2, all the way vn, and this is the smallest, okay, this is called, it's a basis if it's linear, if all the vectors are linearly independent, and that the span of the set of vectors is our entire space V. And so this set here is just the smallest linearly independent spanning set. It's not necessarily unique. Not necessarily unique. Okay, real quickly, let's touch on nullclines. So there's 2 types of nullclines and then equilibrium points. So we've got V nullclines, we've got H nullclines, and we've got equilibrium points. So V nullclines are where dx dt is equal to 0, and the direction of your arrow, so direction, whether it's pointing up or down, is determined. You can determine that from the value of dy over dt. H-null clines are when dy over dt are 0, and the direction of the arrow, whether it's left or right, you get analogously from dx over dt. Equilibrium points are where, oh man, this iPad. It's when dx over dt and dy over dt are both 0. Okay, last two definitions, we were going to talk about column space and null space. So column space is just the span of your column vectors, span of column vectors, and your null space, sometimes denoted as an operator null of A. I'm going to write out a formula first, and then we're going to talk about what it means. So this is the set. This is a set. Man, the set of all x's in our space, our n-dimensional real space, such that our solution x satisfies the equation ax is 0. And so in general, the dimension of your null space is the number of free variables. And so this is just the space of the solutions to the equation a of x, ax is equal to 0. Cool. That should cover most of the topics that will show up on your exam. Best of luck.